All right, so welcome to the Altium Workshop on November 5th, November 6th, 1955. Sorry, no, it's 2021, whatever. I'm going to share my screen on Zoom here. So I've just got a couple quick slides here just to introduce what a printed circuit board is for those who may be unfamiliar. A printed circuit board is a laminated structure of like layers of metal and insulating layers. So your metal is copper. Your insulator can be many things, but it's often fiberglass. That's pretty typical. It's cheap and it's just the most common. There's of course different kinds of fiberglass that have different dielectric properties, but suffice it to say, some kind of fiberglass. And then on the outside of the board, you solder your components onto it later. And the PCB is both a mechanical device, as in it mechanically holds components in place, but it also provides electrical interconnect with the metal. And you can have many, many layers. Serious PCBs can have more than 20 layers. Really cheap PCBs might have one layer. It's always an even number just because of the manufacturing process. It doesn't make sense to make an uneven number of layers, except when you have only a single layer. That's sort of the exception. This is a little diagram of some of the steps. It's sort of a simplified diagram of making a two-layer PCB, and there can sometimes be more steps. So you start with like a double-sided copper-clad laminate. So you've got like the fiberglass material and then thin layers of copper foil on the outside. First you make a pattern, and then you usually at some point you plate up the thickness. After you've etched the pattern that you want, you plate it all up. And you can see that step is really critical because that's what allows you to get plated through holes. And it also makes the copper a little bit thicker, which is also nice for having good electrical conductivity. And they've got some other steps, and it's sort of abstracted out, but I guess what I was trying to get at here is that there's a lot of steps involved, but fortunately for us, fabricators can do it pretty cheap. So let's talk quickly about layers. Here's like a little cross section of a board up on the top right here. This is a 4-layer board, obviously. The number of layers is talking about the number of metal layers. In this case, this is a 4-layer board. We really won't do anything more than 6 layers. 4 is pretty common. And you don't put components on the internal layers. I know some people don't get that right away. So I just wanted to make sure it was clear. All the components go on the outside layers. And then so you can see the construction here involves like this fiberglass core and then these 2 what are called pre-preg layers, which are just mean it's sort of this fiberglass that has this glue in it that you have to heat up, and that when you laminate it together, you apply heat and pressure, and that it's fiberglass that's pre-impregnated with this sort of glue that gets hot, or when you heat it up, it sets. These are all details. It's just important to know that that's how that works. And it's important to know also that the prepreg is incredibly thin. And I mean really thin, like it's a sheet of paper thickness. It's really thin. That might be important to know, for meeting, IPC regulations for voltage, withstanding voltage or something. And your core layers, usually much thicker. Sort of a typical thickness of like a final thickness, usually about 1.6 millimeters for the thickness of the board. And the prepreg layers might be like 0.2 millimeters thick or less. I know on this board, in sheet of paper. Yeah. Another important thing we need to know about are vias, which are simply just plated holes that connect your layers together. So you can jump a signal from the top layer down to the bottom layer or to any layer in between. And they really make complex designs possible. And you can see in this diagram that there's blind and buried vias as well as through-hole vias. Don't use blind and buried vias unless you absolutely have to. If your design on this team uses them, we won't be able to afford to make the boards. Like the cost of production just goes up a ton when you use blind and buried vias. So even like high-end boards that have really demanding, like a lot of the times if you want to, like sometimes it's nice that you want a blind via because you don't want a net antenna. So instead what they'll do before making a blind via, they'll make a through-hole via and then back drill the hole so they can eliminate that antenna. So like manufacturers or designers go to real lengths to avoid blind and buried vias. So I also included this little table here just to give you some idea of common via sizes. When we're talking about the diameter, like the via has this ring called the annular ring, and then there's a hole in the middle. So you drill this hole out, that's your drill diameter. And then the outer diameter here, that's the via diameter. So you have the drill size, which is the hole, and the diameter. Now the actual hole size will be smaller because you're going to plate it with copper, but it doesn't matter really. You don't usually care. So like a small via is, usually small and medium vias are what you want to use. Yeah. Usually it's when you care about minimizing, well, it's either you have a really dense design and you have a part on top and you can't afford to have the through-hole via interfere with the routing of that part. Or it's for signal integrity where you have a really high-speed signal and you can't afford to have an antenna. So what I mean by that is if I have a stack up of a board, so these are my metal layers, and I'd like to jump a signal down onto this layer. So I've got a via going all the way through, or if I had this, my signal will go through here onto here, but then you have a stub, which in the RF domain, this looks like an open circuit on a piece of transmission line. So you're going to see a reflection of that signal at really high speed. This is like in really demanding designs. You may choose to have a blind via that eliminates the rest of this and it just jumps from the two layers you need. But like I was saying, like manufacturers will sometimes, designers will sometimes have employ a technique called back drilling, where they just have a second drilling step, and they drill out the copper to make it kind of like a blind via. That's for the more esoteric reason you might do it, but usually it's for like really dense designs when you can't afford to take up space on another layer when you're not using that via on that layer. Yeah. So yeah, blind and buried vias, it's good to know they exist, but the chances are you won't. Only on the most demanding designs would you ever use them. I think that's really all I've got to talk about, generally speaking. So with that, we will go straight to Altium now. So this is Altium for me. You know, yours probably doesn't have all these projects open on the left. But when we're doing a design, I mean, your workflow goes like this, you know, file, new, project. You know, I could pick a project, give it a name. And I'll put it somewhere sensible. So I'm just creating a project. So now it's appeared. My new project is down at the bottom. Down at the bottom here. When I have the project, the first thing we do with any design is we need to draw our schematic. So you're going to add to your project a new schematic, and it will do that. Thinking. Yeah, sure. You just hover over your project, you right click on it, and then add new to project and schematic. And we're just going to save this. So Control S or File Save, and call it whatever you want. We're not going to make a very involved schematic, but I want to, what is important to get across here is that the schematic is the driving document of the whole design. So you put, it not only has the logical connections between pins on a component, but it also links a footprint, you know, that's going to go on the PCB. It links that to to every symbol on the schematic. What circuit should we make? I was thinking of a 555. I think I've got a 555 in here. You do? I'm not a. The what? Schematic list? That's a tool that I'm not actually very familiar with, but or not one that I use a whole lot. I know that I guess I don't have that. Where's that? Schematic list. I guess it's listing, you know, objects in the document, and we don't have any yet. You could if you want. Yeah, we're not going to use it. So yes, you can close it. So if you've got your libraries installed, you'll see the libraries, you know, when you click down here. So if I go to like analog, you know, we do have the 555. If you don't see, you know, if you don't see a lot of like useful information here, you're going to want to right click on this and hit select columns. And once you do that, you can select things like, you know, maybe I want manufacturer part number. Probably don't care about design item ID, but definitely description and definitely footprint. Yeah, so there we go. I've now got a manufacturer part number, footprint, and a description. That's usually pretty good. So let's grab ourselves a 555 and place that on the schematic. You'll notice now, if I double click on this and you scroll down, you can see there's a lot of attributes that or parameters, including most notably a footprint that is linked to this symbol. It's thinking about showing us the footprint. So that's like the, come on, think and show us the preview, please. Okay. Oh, there, so, you know, there's the footprint that's going to end up on the PCB in not too long the time. Yeah, I wasn't going to make a very complicated schematic, but let's, like, you know, so some of the important things you'll need are going to be like power and ground. And you can find those on this little toolbar here. If you hover over this ground symbol and right click on it, you can now see all these different ports, these different power ports that you can use. So if I wanted to place like the ground port, I can easily select that. And you can also come up here and place a wire. You can place other things like a net label, but let's place a wire and connect this ground port to our device. So a wire is just a logical connection between 2 points. And you can see just like every pin on this symbol corresponds to a physical pad in this footprint. So that's a, you know, that's a necessary thing needs to be correlated. So let's place also, let's say we're going to run this on 5 volts, I guess. Seems reasonable. Oh, here's a neat little shortcut. If you hit P on your keyboard, it brings up the place menu. And then if you hit W, that'll select wire. So you can place wire by hitting E and then W. So that's a neat little trick. We'll tie reset high, like so. What's the simplest? So let's get a resistor in here. I think we want a resistor. Find a resistor. So similarly, you know, resistors come in all shapes and sizes. Two of the most common ones that we use are called 0603 and 0805. Those are just what those mean is, let's draw ourselves a little resistor here. They're saying that they're giving you the dimensions of the part. 0805 means this is 0.0. Yeah, doesn't mean it's 0.08 inches. Yes, inches. And 0.05 inches, like that. It is imperial, and it's kind of weird how we use a mix of imperial and metric, but it's just kind of the way it is these days. So this would be an 0805 package. Of course, it's not to scale, but needless to say. A smaller size would be an 0603. Like that. You can imagine this is 0.03 inches by 0.06 inches. For stuff that you're placing by hand, I really wouldn't go any smaller than 0603 as a rule of thumb. Any smaller than that gets really tedious to place. So 0603 is the smallest you should go. But let's be generous. Let's pick an 0805 resistor. Let's make it 1 kilo ohm. So I'm going to type in my search bar 1K, maybe space ohm. Now you can see it's finding me lots of resistors that match that pattern. Here's a 1 kilo ohm 0805. That looks good. You can see the footprint there for it. So I'm going to place that here. Like so. Be tied high to our discharge pin. See, can I make an astable oscillator from memory? I think I can. I don't know what frequency it's going to oscillate at, but let's pick a 100K, also in an 0805. I'm going to drag this over a little bit. And now we need a capacitor to complete this circuit. So let's look under our capacitors library. 1 microfarad. That will be interesting. 1 microfarad. And again, let's pick an 0805. It doesn't have to be. Now, another thing about capacitors is they have a voltage rating. That's important to know about and to think about when you're selecting components. We're not using a very high voltage, so I'd pick like a 25 volt rated capacitor because why not? No point in going lower than that. Yeah. Yeah, there's less derating as a function of voltage, for one thing. That's really the main thing I would say. If it's rated to a higher voltage, it will derate less as you apply more voltage to it. So of course, in this case, we're only applying 5 volts. So it's like not a big deal, but if you're even, I think if you're even like halfway to the voltage rating of a ceramic capacitor, you're already down like 30% of the value. So I'd say there is some benefit to picking higher voltage ratings. I definitely wouldn't want like a 10 volt capacitor here or a 6.3 volt. You know, that then it would be derated by quite a bit. Yeah. So I think that looks to me like an astable multivibrator. Control pin should get bypassed with a little, let's give it 1,000 picofarads. 0805 again. I know I'm going through this fast, but we only have an hour and I didn't really come with the schematic already. But I thought it'd be useful to show you the process of making a schematic. We'll keep it pretty simple. I just want to go through the workflow a little bit. Let's say, okay, finally, I don't want to actually, because this is a useless circuit. Well, it's not useless, but it's not going to do anything. I'm going to say that I don't want to use the output. So I need to put a no ERC flag on the output so that when the ERC runs, it won't flag that as being an unconnected net or node rather. So that's a nice thing to do. Oh yeah, so I'm just saying I'm not going to use this pin 3 just because we're not actually doing anything with this circuit. So you want to place what's called a no ERC flag. so that it will tell the electric rule checker or electrical rule checker, the ERC, it'll tell it not to flag that as a problem. So now there's a step, the final step, once you've kind of laid out most of your components, you're pretty much done. You need to do what's called annotating the schematic. Because right now, if I wanted to, you know, these all have like C question mark, R question mark. That's not very useful for uniquely identifying the components. So you need to annotate the schematic. You can do this in a single step, in fact. If you go to Tools, Annotation, Annotate Schematics, we can now hit Update Changes List. It says, okay, 5 changes were made. We're going to accept those changes and create this ECO, which is an electrical engineering change order. It says it right at the top of the dialog. So it's going to annotate the schematic for me, basically. So you can see all it's telling you that all the question marks are going to numbers. So we'll say validate. I mean, we know it's going to be fine, and execute. And that's what actually does it. That's what actually annotates it. Now that we've done that, you can go back and you can see now we have little numbers next to every component, which is necessary for uniquely identifying the components. So now that we've got that, you know, obviously it's not a very exciting circuit, but we're going to make it TV now. It's going to be a great one. And why not save the project while we're at it? And save this. Okay, so there's a few, what you'll do is you'll right click like we did before on the project, add new PCB. Let it think for a minute. It's thinking, there we go. Okay, make sure to save this document right away. Okay, so now I've saved it, and really before we do anything else, even before you add your components onto the board, we really should do a few setup steps. So first I'm gonna, you know, go into properties. I want to change my units to millimeters because I like to work in millimeters. So I want to do that. You know, just go to properties, scroll all the way to the bottom, select millimeters. What we also want to do, you may notice you don't have this little toolbar. If you right click on this empty space up here, you can then select utilities. Go ahead and do that. Mostly what this gets you easy access to is the grid manager button. So I can set my snap grid. And a snap grid is basically when you're moving stuff around on the board, it snaps to a grid. It's like this imaginary grid that overlays the board. So I'll set, right now it converted the imperial to metric. So let's make this like a 0.1 millimeter snap grid. That's a reasonable snap grid to use. So we've done that. We can now, there's another thing to note. Well, we can do that later. Yeah, at this point, let's bring in our components. So you're going to go to Design and Import Changes from Name of Project right there. And you can see it's telling you everything it's going to add. One thing we don't want to add, in fact, well, I'll go ahead and let it add it, but there's this thing called rooms in Altium, which are simply a way of logically grouping components together on the board that I don't personally find very useful. I think that it's just kind of, yeah, I don't find it useful. So I always delete the rooms, but I'll show you what they look like and then we'll delete them because I just think they're kind of useless. So you can hit validate and it'll validate things and then finally hit execute. And there brings the components in. Now you can see all our chip and our 4 passives have appeared inside this translucent red rectangle. Select the translucent rectangle and hit delete. All right, isn't that better now? Like, look at this. What happens if you have this room and then I move a component? If I move a component outside the room, it gets angry at me. And I'm like, well, okay, so that means I have to resize the room to encompass all the components. It's like, what's the point? There are more useful ways to group components together and apply rules to them, like net classes, which I like, and component classes and things like that. I just don't think the rooms are very useful. Don't worry about them. Something we want to do is actually change our origin for our board. The reason why we want to do this is if I try to move a component, I can't actually move it to the left or down, or below the original origin. I have no idea why that's a thing, but it is. So anyway, we're going to change our origin to be somewhere up here. So what we'll do is say, what is it? Edit origin and set the origin. Set it right there. Cool. Now all the dimensions on the board, all the location, the coordinates on the board are now reference that new origin that we have placed. At this stage, you're probably going to want to set up your design rules. And setting up your design rules is one of the most important steps in the whole process because, well, let's just go there and look at it. Well, lots of things, right? There's a lot of rules that define things like, how close two components can be to each other, or how close a track can be to something else, or how thin the traces can be, or bizarrely what the maximum trace thickness can be, which I don't know why it exists, but so this is sort of where you apply. Like I said, it's one of the most important steps, applying these rules. So let's start somewhere like in the clearance rules. You can see the default has it at about 0.25 millimeters between different things. So there's saying track to track can be 0.25 millimeters. And everything else also 0.25 millimeters. And this may be okay. That's not super mega close, but you may, in some designs, you may want a more generous clearance between things. Or you may want it to be tighter, especially with SMD pad to SMD pad. You may want this to be like 0.15. Now you may say, well, how do I know what it's supposed to be? And that's where you go to your manufacturer or whoever's fabricating your boards, and you look up what their capabilities are. That's the first place to start. You make sure that they can actually manufacture down to a small enough tolerance that you can actually make all the features on your board. So if we went to, like, say, JLC PCB, for example, they've got a rather nice capabilities page. So they tell you things like, maximum dimensions, thickness, tolerance, but this is all for like the board itself. But we're interested in things like, what about minimum clearance? That might be useful. So it tells you things like pad to pad clearance. And look, that's quite small. That's pretty good. You can make a lot of footprints with a 0.127 millimeter pad to pad clearance. You got pad to pad clearance. You know, there's all kinds of different rules you can set up. I mean, and they make it seem a lot more complicated than it really is. But here's an important one, you know, pad to track and pad to pad. But, you know, like realistically, what's the difference between pad to pad clearance and pad to track clearance? Like it's ultimately just the etching of two copper materials. It has more to do with the fact that this pad has a hole in the middle of it, and you might be worried about the tolerance of that, of the drilling of that hole and things. But you know, you also don't necessarily want to have your clearance like all the way down to the minimum. Just because you can go down to 0.2 millimeters doesn't mean you necessarily want to. So for this design, we'll leave everything as is because I think these are okay. The low voltage stuff, they're okay. And we don't have a super demanding like pad to pad clearance needed. So we're gonna stick with this. We gotta look also at our width rules. Let's go here again. What's minimum trace width and spacing? You can see the minimum spacing on say a 1 to 2 layer board is 0.127. Okay. On our clearance for track to track is 0.25. There's no need in our design to go down so narrow. We don't need to put our traces so close together. There's really no reason to do so. So we'll leave that as is. But width, we were looking at width. So the width, minimum trace width is 0.2. That's for, oh yeah, that's for, no, it's not. I'm sorry. It is actually 0.127 for a 1 ounce copper outer layer on a 1 to 2 layer board. Okay, because this is going to be like a 2 layer board, let's say. We can specify this as, let's say we don't want to make anything smaller than like 0.2. And let's say our preferred width will be 0.25. The maximum width, I don't know why this even exists, but it does. Make this something really large because there's no practical reason to have a maximum trace width. I just don't know why it exists at all, but it does. So make this like 10 millimeters. You might go, the next thing to hit is our Polygon Connect. We haven't discussed what the polygon is, so maybe we'll do this later. Okay, so let's say that's all for now. So let's real quick, let's just slap these together in some haphazard fashion. I'll put that there. As you're placing components, you want to also take care of their designators. Making sure that the designators are going to be somewhere rational. Yeah. Ah, yes. So as I'm dragging, when I want to drag a component, I'll click and hold this, then I can drag it around. Hit the space bar to rotate. Space bar rotates component. And the same, I mean, anything you want to rotate, just hit the space bar. Okay, so this is there's a layout. Good enough. Oh wait, we missed one. Oh yeah, let's just do that. Now we kind of see, once you kind of started laying things out, you can see how big the board is going to end up being. Obviously, it'd be nice to have some mounting holes probably. But before we do mounting holes, well, actually you want to do mounting holes. I usually do mounting holes like early on because you don't want to forget about them and then have to, you know, stuff them in somehow. If you want to place a mounting hole, right click on this up here and hit pad, and you get a pad, and we can give it any designator. We can assign it a net. We could say, let's ground our mounting holes. Oops. Ground. Out. Okay. We can give it like a size, just like a via. You know, you've got like an outer diameter, and then you've got a drill diameter. So I've made this one 2.7. So that's like for like an M2.5, which is a pretty common hole size for like hobbyist stuff. So that's a reasonable mounting hole. So now let's place it. Let's place it right. Let's place it right there. And let's put 4 mounting holes around the corners because we want to make sure that our 555 astable multi-vibrator is very secure. Okay, and you'll notice when I copy and paste works just fine, but it doesn't preserve the net. So you have to reassign the net when you copy and paste. Oops. I'm just placing these. We're going to get to the bit where we finally define our board outline in just a moment. Okay, so suppose, did I get those in line? If I didn't get those lined up, I can select them both, right click, align, and I can align to left, let's say. Okay, so that aligned them to left. And I can select them both and go to properties and modify the properties for both of them at the same time. So I can give them both a ground net. All right, so obviously we've got a bit of spare space on this board. It's a little big for the design that we have. So I'd say we need to define our board size. So usually I like to do this in the mechanical 1 layer. You go to the mechanical 1 layer, and then you go to like place line. You can then draw lines. As you're drawing the line, hit the tab key. You can specify the width of the line. Make it something unique, because I'll show you why in a moment. Let's make it 0.05 millimeters. A fairly unique line width. And I'm going to draw my 4 lines with corners. Okay, so we have a board outline drawn. I just sort of roughed it out. If I select one of these, you know, I could go around and hold down shift and I could select all the other ones. That's a technique you could use. But if I had like a really complicated board shape, I could actually select one, right click on it and say find similar object. Now we can specify, let's say I want it to be stuff in the mechanical layer, things with the unique width is 0.05 millimeters, same. Look at that, it selected them all for me. So now they're all selected. I can now go to design, board shape, find board shape from selected objects. Boom, it's a Christmas miracle. We've got a board outline. So let's now, if you hit the 3 key, just the number 3, you can jump to this this view of the board in 3D. You can see there's some things we need to fix up yet. Well, pretty much it's, you know, we've only done the bare minimum so far. But I think we're getting close to the end, where GB will start for. But I think we covered a lot of stuff. Does anyone have any questions at this point? Yeah. It was just because I wanted holes in the four corners. That's my mounting choice. So you may have a different idea for how to mount the board, but usually I think, you know, I could for such a small board, I could like probably put one here and one here, or I could put one on each corner. But I just figured for like I just wanted to give a sort of example. It doesn't have to be that way, but that's four corners, mounting holes on the four corners makes sense to me. That's all. I've never talked about vias, but placing vias is just like placing a pad. You just right click here, place via. And then if I want to make, it's often good practice to place a via at every ground pad, so you can ensure a good low impedance connection to ground. So that's a good thing to get in the habit of doing. If I want to do that, I can place it there and have it overlap that pad. It'll adopt that ground net. Now I'll just drag it off the net, just like that. Placing tracks, you can go up here to route, interactive routing. And now I can, well, I have to be sure I'm in the right layer, of course. Interactive routing. And, you know, it's just drawing lines. And again, just like as you're drawing the line, you hit the tab key and you can change the width to something else. So I made it 0.25. So I like that width. And then it's just drawing lines. This is the artistic bit. Yes. Anyway, I didn't get to cover polygon pores, but maybe that'll just have to be a lecture for another day. So, all right. Are there any other questions that I can answer at this point? So we went through, you know, basic schematic capture, basic rule setup, and board definition and all that. I mean, this has only really scratched the surface, but I encourage you guys to play around with Altium on your, as you wish. You know, you got the licenses now. You can find a lot of resources online as well. You can always ask me. I have some videos on our YouTube channel also that I've made similar to this, you know, maybe a little longer even. And I made one video where I just laid out like a board and ran through it like really fast, like in 4 times speed or something. So that's there. You can check those out. All right, that's all. Thanks everyone for coming, and hope this helped.